So guys, this is CodeNCode, and in this lecture we are going to implement fast Fourier transform algorithm. For the past four lectures, we have been studying the theoretical concepts of FFT, and now in this lecture we are going to implement it. And also, I'll give you some practice problem that after implementing this algorithm, you can go ahead and try to solve those problems yourself. All right, so let's get started. So you might remember this pseudocode from the last lecture. All right, let me show you how the pseudocode will transform into an actual working algorithm. Right. So let's come here. So first of all, how this works. All right. So we have multiple test cases. That's why T. For each test case, I'll give you degree of the polynomial. I'll be giving you two polynomials, A and B, of degree n. Right. Then you have to multiply those two and then return the result or print the result. That's what we are going to do in this lecture using FFT algorithm. So we are going to implement FFT algorithm, right? Now, once you read n, you define two polynomials in coefficient form. That's why you have n plus 1 elements in A and B. Then you read A and B, n plus 1 elements, right? And then you multiply A and B, both of which are in coefficient form. Then you get the result back in coefficient form, and which you can print, right? As simple as that. The important part is this multiply function, right? So this is your multiply function. So how does it work? So you are passing two vectors a and b, basically two polynomials in coefficient form, right? Now if you remember, what we are going to do, we are going to evaluate the polynomials in complex plane, right, using complex numbers, and these are real numbers. Both of polynomials a and b are in real numbers, right? So what we are going to do, we are going to convert a and b in complex form, right? A and b both. We have defined fa and fb, basically polynomial a and b in complex plane. uh, Instead of vector of int, now they are converted into vector of cd. What is cd? I defined a new type, complex type, right, which is complex double. So let me just show you here. CD is basically, I've defined the new type CD, that is complex double. So complex double means, first of all, this is a complex number which will have two things, real part and imaginary part, right? And a complex number you write in a form of a plus ib, right, where a and b both are numbers. So when we say complex of double, we are saying that a and b will be of type double, right? If you say complex of int, a and b will be of type integer. That means you can have numbers like 3.5i, but you can't have 3 plus 4.6i, because 4.6 is double. But we know that in our calculation, a and b can be double. That's why we have defined a double data type. We have defined a complex number of double data type. That's why we are calling CD. So CD means complex number where the numbers a and b can be double. Basically, we can have floating point integers, right? So we have converted a and b from vector of into vector of complex number. Basically, in the complex plane, we have converted a and b, right? Once we are done with the conversion, we will calculate the nearest power of 2. Why power of 2? So you remember in the lecture I told you, I'll tell you the reason why we go with power of 2. So in recursion, what we do, we keep on dividing n by 2, right? You have a polynomial that you want to be evaluated on n points. You make recursive call and divide n by 2, n by 2, n by 2, n by 2, keep on going, right, till you reach 1. That will be our base case, right? So if n is not power of 2, there will be some point where you will be stuck and you won't be able to divide that number by 2. For example, let's say uh, 20 you can divide by 2. 10 divided by 2, 5 you won't be able to divide, right? So you won't be able to divide. That's why when we are implementing FFT, we calculate the nearest power of 2, right? So what we do, see, a is having degree a dot size and b is having degree b dot size. The result will be having degree product, or basically addition of these two, right? So when you are calculating n, basically number of point on which you want to evaluate the resultant, right? Since the resultant will have degree a dot size plus b dot size, right? So n should be greater than that. You remember, if a polynomial is having degree d, we need to evaluate it at least on d plus 1 points, right? So since the result will have degree this much, a of size plus b of size, n must be greater than that, and the number of point on which we want to evaluate, right? It must be greater than that. So as long as n is smaller than this, we will keep on keep on multiplying n by 2, right? So just keep on multiply n with 2. So this is one way to multiply n by 2. I'm using the uh, left shift, right? It is another way to multiply any number by 2. Left shift only once, right? And it is faster. That's why I'm using this. So finally we have when this while loop completes, we'll have n, which is a power of 2, and will be greater than or equal to this, the resultant degree, right? Now what you will do, a and b you can just resize, right? Initially if both of these two are having degree 2, resultant will have degree 4, so a and b needs to be resized to 4, right? And at the end, when you are resizing it, at the end you will be having zeros appended, right, in complex plane, of course, because fa and fb are complex numbers, right? Basically vectors of complex. So the extra element that you are appending will be 0, and when you append 0 in a polynomial, it doesn't change it. For example, 2 plus 3x square, 2 plus 3x, right? So when you have 2 plus 3x, coefficient of x raised to power 0 is 2, coefficient of x raised to power 1 is uh, 3, right? And then if you keep on adding 0, it's basically 0 times x raised to power 2 plus 0 times x raised to power 3 plus 0 times x raised to power certain number, right? So if you keep on adding 0 at the end, polynomial doesn't change, right? Because 0 times x raised to power 3 is 0 itself, so polynomial doesn't change. So when we resize, we are basically appending zeros at the end, right, which doesn't change our polynomial. So original polynomial are still intact, and we have basically increased their size because we want to evaluate them on these many points, right? So what you will do after that, you will apply FFT and evaluate FA and FB, right? Basically converting A and B from coefficient form to value form so that we can multiply faster. Remember? So this A and B are in coefficient form. We perform uh, FFT and now they are in value form, right? So we have applied FFT on FA and FB. Now FA and FB are in value form, right? I'll explain this FFT function also. This is the very important part of FFT, right? Once FA and FB are in value form, multiplication is easy. Just run a loop till n, and FA is equals to FA times FB, right? Each value you can simply multiply, that we have seen in the very first lecture, right? So multiplication is done in linear time. Remember, convert them in value form, multiply in linear time. Now since I have updated fa itself, so fa is your result, right? And then you can revert it back into coefficient form because fa is again in value form, right? See here, a and b are in value form after applying FFT. We have performed the multiplication. Now the result is in value form, but we want it in the coefficient form. So what we'll do, we'll apply the inverse FFT. So here you have your result after applying inverse FFT. Here you have the result after multiplication, and now we want FA in the coefficient form. So what we'll do, we'll apply inverse FFT. I'll explain both FFT and inverse FFT function. So let me explain it now. So what we are doing, in the FFT function, we are evaluating polynomial fa on n different points, right? Let's go here and have a look at the implementation of FFT. So the implementation works something like this. So we have function that takes polynomial and n on which, and the number of points on which you want to evaluate this polynomial. The base case is if n is equals to 1. When n is equals to 1, that means you want the polynomial to be evaluated on 1 point. That means degree of polynomial is 0. That means the polynomial only has a constant term, right? For example, y is equals to 5. It has only one term, right? Degree 0 polynomial. If you have this type of polynomial, you don't have to evaluate it because it only contains the constant point. constant number, right? So if n is equals to 1, return the polynomial itself. You don't have to evaluate it. So this is our base case, right? Now, if that's not the case, here comes the recursive part. What we'll do, we'll create basically we'll divide polynomial p into pe and po. We have learned this in the previous lectures. If you haven't watched the previous lecture, please go ahead and watch lectures 1 through 4, right, before coming to the implementation of FFT. So we'll create pe and po, right, and we'll go through each of this each of the term of polynomial p, and the even degree term will insert into PE and odd degree term will insert into PO. That's exactly what I'm doing here by running loop till n by 2 only. You can go through the whole loop, and if I is equals to if I is odd, insert in PO, otherwise insert into PE, right? You can do it this way also by running the loop till n by 2 only. So now we have PE and PO. What we'll do, we'll make a recursive call to evaluate PE and PO, right? On how many points? N by 2 points. That's exactly what we are doing here. So now P and PO have been evaluated and saving the result back into P and PO, right? Now these two are evaluated. Once they are evaluated, you remember, this is how we are going to utilize them, right? Let's come again here, and here comes the evaluation part, basically utilizing PE and PO to evaluate original polynomial. So first of all, since we are going to evaluate it on n points, so each root of unity will be at 2 pi by n degree apart, right? We have seen this, so I have calculated the angle that will be 2 pi by n. And what is pi? I have already defined pi here. You can calculate the value of pi using cos inverse function. So cos inverse minus 1 is pi, right? So I've calculated the angle 2 pi by n, right? And now if we'll calculate it, we will calculate w is power 0, right? The very first root of unity is w is power 0. The second one is w is power 1, w is power 2, so on and so forth. These are, right? So here there is w is power 0, w is power 1, 2, 3, so on and so forth, right? So I've defined w is power 0, which is the very first root of unity, because we are going to evaluate it on root of unity. The very first root of unity is w is power 0, which is nothing but 1 plus 0i, right? You can directly write w1, define complex number w1. w1 means real part is 1, imaginary part is 0. You pass pair, right? And imaginary part, since we are not passing, it will be 1 plus 0i. This is my very first root of unity, and this is w raised to power 1. W raised to power 1 will be what? Cos of angle plus I sine of angle that we have just calculated. Remember, that will be your w raised to power 1. So since we have these two, right, we can go ahead and implement this part, which is this, right? So again, we'll run a loop till n by 2, right? We'll evaluate p of I and p of I plus n by 2, right, using this formula, and pe of I plus w times po of I. Here I have written w raised to the power I, right? And w raised to the power I we have already defined, right? So initially when I is equals to 0, it should be w raised to the power 0, which we have defined here. In the next iteration, it will be w raised to the power 1. How? W raised to the power 0, if we keep on multiplying it, w raised to the power 1, it will keep on getting into the next power, right? So in w, if you multiply this w delta, it will become, initially it is w raised to the power 0. You multiply the delta, which is nothing but w raised to the power 1. So this will become w raised to the power 1, multiply it again, w raised to the power 2, multiply again, w raised to the power 3, so on and so forth, right? So each time when we are coming here, w is actually w raised to the power I, right, because of this. So we are evaluating pi and pi plus n by 2 using the exact same formula that we have discussed here, and we are done. Finally, we have p evaluated and you can return it. So this is your FFT. Now what we are left with? We are left with inverse FFT, and let's have a look at that also, inverse FFT. So as we discussed in the last lecture when we were discussing the inverse FFT, If you remember, here is your inverse FFT. It is exactly the same as the original FFT. Only difference is that now the powers must be in negative. Power is negative, that means the angle must be in negative, right? So if you go here, it is basically simple copy paste of FFT function. Everything is same. Base case is same, PE and PO are same, right? Their evaluation is same, everything is same, except when you are calculating angle now, it is negative. Earlier we have 2 pi by n, now we have minus 2 pi by n. That's the only difference. And you have here everything same. So this is your inverse FFT. Now since you see that there is a lot of similarities between FFT and inverse FFT, you can actually combine both of those functions and just need to pass one extra variable here, whether you are performing FFT or inverse FFT. You can provide a boolean value here, right? And you can combine these two together. I have created these two different functions just for the simplicity to understand. So yeah, this is how you implement inverse FFT. So now if you come back here, you apply FFT to FA and FB, perform the multiplication, convert the result back into coefficient form because result here is in value form. Apply inverse FFT and convert the result back into coefficient form. And you remember, sorry. So the result again has two parts because FA is what? Is a vector of complex number. It has both the parts, the real part, imaginary part. But when you have converted it back into coefficient form, only the real part matters. Alright, the imaginary part not. So you take the real part which represents your coefficient in the coefficient form and divide it by n. Why? You remember when you are performing inverse FFT, you perform basically the same the way you do in FFT, perform the multiplication with the negative powers, and we also got a multiplication factor 1 by n, right? So perform FFT and each element divide by n. So that's exactly what we are doing here. For each element we are dividing it by n, and that gives you your final result, right? Because we have multiplication factor 1 by n, so you must divide it by n, each value, right? So result of I is equals to, take the real part of your resultant, divide it by n, compulsory, and round it off, because when you're calculating the result, it's actually in double, right, in floating point integers, but we want the result into the integer, right? So that's why you must round it off. And that's the reason actually for bigger number, for larger number, FFT is not very accurate, right? Because while performing the round off, you might not get the exact result. So for bigger number, it's not very accurate. Alright, so divide each number by n and round it off, and there you have your result, and finally return it back, right? So this is how you perform FFT. Now let's go ahead and run it and see it in action. Alright, so let's have a look at the test cases. So the first test case is this. So let's go, I have written down two different test cases. Okay, so let's go with the first test case. So let's run it, compile and run. Right. So initially we have, my bad. So first of all, let's say there will be two test cases, enter. And in each test case, in the first test case, degree of each polynomial is 1, right? So I'll write 1. If degree is 1, for each polynomial we will provide 2 values, right, their coefficient. So since degree is 1, for first polynomial coefficient form will be 7 and 2. For second polynomial coefficient form is 4 minus 3, right? And here's the result. So if you multiply 7 plus 2x and 4 minus 3x, the result you get 28 minus 13x minus 6x squared. That's exactly what we are getting here, right? 28 minus 13 minus 6. Alright? Let's have a look at the test case number 2, which is this. Okay, so let's go with the second test case. Okay. For the second test case, again, degree is 2, so we'll plus 2 here. My bad. Okay. Let me just make it a bit smaller. Okay, yeah. So 2, right? That means for each polynomial we have to provide 3 coefficients, right? So 3, 2 and 1 for the first polynomial, 3, 2, 1 coefficient of first polynomial. For second we have 1, 2, 3, so 1, 2, 3, enter. So the output is 3, 8, 14, 8, 3. 3, 8, 14, 8, 3. As you can see, this is working just fine, right? So yeah, this is how you implement FFT algorithm and perform polynomial multiplication in analog and time. All right. So I'll provide the link of this implementation in the lecture itself. Or if you have any doubt, you can ask me in the comment section. I'll try my best to answer any query or doubt you have. All right. So yeah, this is it for this lecture. And yeah, there's one thing that I forgot. Yeah, I'll provide you the practice problems also. I'll provide it in the description itself. All right, so you can find the practice problems in the description of this lecture. All right, so yeah, this is it for this lecture. Thank you guys for watching, and till the next video drops, keep coding. Thank you.